Well, we talked about perturbation methods last time. I think we're going to hopefully finish them up today. Boundary layer theory next time. So hopefully you see today how that connects. Okay, this is hopefully the most insightful day into boundary layer theory that sort of gives you the math of it works. So what we talked about, we did an example. Okay, we started out looking at a reaction in packed bed with flow. And so we said we're going to have this packed bed and we're going to have flow from this side, from the same side where there's a high concentration. Okay. And we looked at, or we talked about this and we non-dimensionalized the set of equations, the species mass balance. And we got out this guy where we had the Dom-Kohler number and the ratio of the Peclet over Dom-Kohler number. And we said, let's look at the case where we've got the Dom-Kohler number much bigger than 1, and then the Peclet over Dom-Kohler number order 1. Okay, so what that means is that we have a fast reaction, but there's also significant flow. Okay, so diffusion is relatively small, but everything else is kind of big. All right, and so what we saw was that then that meant this, the 1 over the Dom-Kohler number that comes out here is a small number. This one's not a small number. We called it something else, so we didn't have to write it Peclet and Dom-Kohler all over the place. We called it alpha, or 1 over alpha. So then we said, okay, now let's apply the perturbation techniques that we learned in the regular perturbation and asymptotic expansions to try and solve this. And the reason we need to do that is because this is a nonlinear equation here. So if it wasn't nonlinear, if this was linear, we could just, it would just be sums of sines or cosines or exponentials, right? Depending on what the values of the eigen, or what the sign of the eigenvalues would be. But it's not, it's got this p squared in there from the reaction because it's a second order reaction. So we're kind of stuck unless we do something else. Okay. So we said, okay, well, we'll apply this. So we put in our expansion. So we use an asymptotic series, which is an expansion in the small parameter. And we plugged that in and we got out this series now of differential equations. And so asymptotic expansions are great because they allow us to get rid of that nonlinear term, but asymptotic expansions stink because they make for a lot of work, right? So instead of having one problem, we have multiple problems. Now we have a whole series of differential equations we have to solve. So we have one at order 0. Notice that the order 0 problem here is what happens if our epsilon, goes to 0, right? If we have no perturbation from this piece. Okay, so when we have nothing here, we end up with this problem. That's the same as that one. That should make us feel pretty good, okay, that we did that right. Then we have the next term, which is now if we add a little bit of that perturbation on, how does that work? Okay, and we get something that looks kind of similar here, except we have this, these extra terms that come from the coupling between the 0 and the 1. Okay, and now we got to figure out how to solve this one next. Okay, and so we also have to look at the boundary conditions, okay, and we can apply that expansion to the boundary conditions, and we did. What you'll find for Dirichlet conditions is they always end up here in the top one, okay, and then you get 0 homogeneous conditions down below. The only time it's a little more complicated is if you have some boundary condition that's a function. Okay? So if you have boundary conditions a function, then you have to expand the function as well, something like a Taylor series or asymptotic expansion, and then you're going to get matching at all orders. But we're not going to mess with that. All right, just to kind of give you a heads up. So then you say, okay, well, let's solve this. So we solved each of these, and I solved this one. I think in class we integrated, okay, and when we did that integration, we got minus 1 over alpha x plus some constant, which we called C0 because it's at the order 0, okay. And I said that here's the solution for the second one. I didn't do it. I said you can do it by an integrating factor. So you can do it by an integrating factor. You can go ahead and have fun and do it yourself. Or look up. PSL has this nice table in the back of your book with different ODEs, and I think the integrating factor is like number 2, right? So the first one's like separate integrate, the second one's integrating factor. So then I said, well, this is kind of a problem though. This seems a little weird. We only have one constant, and we lost this second order derivative here, and we only have first order derivative, and that seems wrong. right? How are we going to go about applying the boundary conditions here, okay? And so the point of this is that this happens in what are called singular perturbation problems. So in regular perturbation problems, you don't have this. Everything kind of works out just nice, and you apply the boundary conditions and everything goes fine. But when you have a singular perturbation problem, this is a classic example, we've lost our highest order derivative. And what you can think is that the little change between having zero and having zero diffusion and a little bit of diffusion is actually a big change to the physics of the problem. So before, if we just had a little bit of something else, okay, that didn't change the problem as much. So if you go back and think about the example I did in regular perturbation, we had diffusion and reaction, a reaction when we had no flow. And when you had just a little bit of reaction, then that changed the problem just a little bit. And so if you remember, we had solutions where we had something like this, I guess we had the geometry flipper, and when you had reaction, you just had something a little bit, it just decreased it just a little bit, right? And so that changed the character of the reaction just a tiny bit. What we're going to see here is that in a singular problem, taking away diffusion or adding diffusion makes a big difference, okay? And so, we had this small parameter and go from no diffusion to just really weak diffusion, but that makes a big impact on the physics of the problem. And so that comes out here when we do this kind of perturbation, right? And that difference is what's going to lead to boundary layers, okay? So that's what, that fact that there's that small change is going to lead to a different region where we have to take that into account. And that's what we're going to talk about today. So the first thing I just want to say is, so we can kind of see if we apply the boundary conditions here to these solutions, what's going to happen. So let's think about this for a second. So let's say we're going to try and find C0 and C1. Let's see if we can find those constants. So let's apply to this solution here. We'll do this one first. Let's take phi0 at 0. And what is that? That should equal 0. Well, let's go ahead and apply that. So if we put a 0 in here, we get a 0 for that guy. And now we get minus 1 over C0 is equal to 0. Well, that seems like a real problem, right? The only way that that can be satisfied is if C0 goes to infinity. Okay? So there's some problem at that boundary, at the 0 boundary, right? So over here, there's something going on at that side of the solution that's not right. Let's look at the other one. P0 at 1 should equal 1. Let's apply that instead. Minus 1 over alpha plus C0. I don't have any issues there, right? So I can solve for that. So that should give me multiply over. I'm going to get alpha plus C0 is equal to minus 1. Solve for C0. C0 should be negative 1 plus alpha, parentheses, right? So I have a negative alpha, so I'm just going to pull the minus sign out, 1 plus alpha. Now I can just plug that back into the solution. So P0 at x should equal minus 1 over alpha x minus 1 plus alpha. And I think I rearranged that in my notes to look a little different. Pull the alpha out. Minus 1 over alpha x minus 1 minus 1. Okay? So on the right-hand side of the solution, over here, at z equals L, right, I could resolve the boundary condition. Okay? But on the left-hand side, the boundary condition didn't make any sense, or it didn't work out in the math. Okay, we can do a similar thing with P1, but I don't want to take the time to do out all the math. But we'll find the same thing. So in the phi1 of x case, we have the same problem. Okay. We have that the phi1 at 0 phi1 at 0 equals 0 doesn't make sense. Okay, and you can kind of see that I'm going to get 0 inside the log, right? Okay, so I've got an issue with that. That blows up my answer. My answer doesn't even it doesn't even, it diverges. I have a negative infinity at that point, right? And my constant isn't like a constant here, where I can say, well, that constant must be 0, right? Like the constant is an additive constant. I can't add infinity on to cancel out the negative infinity. There's the real problem, right? But I can find P1, 1, which should equal 0. And in that case, that tells me just that C1 equals 0. That's actually trivial to find, okay? Because I say this thing has to equal 0, and that works out. And so what I find out then is that my final answer, phi of x, is equal to phi naught minus 2 epsilon alpha squared, phi naught squared log phi 0, where phi 0 is equal to -1 over alpha x minus 1 minus 1. Okay, so that's the sort of final answer we get from that sum. And I'm getting this piece here by going back to my sum here, right? So I'm saying phi 0 plus epsilon phi 1. Well, that's what I said here. Phi 0, and then this is a minus sign, so I have a 2 epsilon, right? Epsilon. And I guess to be really rigorous, I should put order epsilon squared at the end of it, right? So there's higher order terms that can make a difference there. Okay. So maybe let's show you this. Well, can you put the screen down? Okay, so this is a plot of the solution. Okay, the dashed line here is the line we would expect if we had diffusion only, just for reference, right? So over here we have 0, right? Over here we have, CA equals CA naught, right? This is a function, this is CA versus X here, right? Where X is Z over L. Okay, the black line is a numerical solution that I generated. So I solved it numerically, solving the, using finite differences. Okay. The blue line and the green lines are the solutions we just found. Okay. So the blue line is only when I have the epsilon 0. So this is just this guy right there. Just that function. Okay. The green dotted line is this one right here, where I add that first perturbation, okay? And I did this for a case where epsilon is only 0.01, so the dot color number is like 100, okay? So it's kind of two things to get from this. So the first is that actually, so it does a pretty good job, right? Our answer gets a pretty good job until about here, and then it's terrible, right? It's doing a terrible job there, okay? The other thing is that actually our epsilon to the 1 is a little bit better than epsilon to the 0, but not a lot better. So it's kind of interesting that even when we just completely neglected the impact of diffusion, you got a decent answer. And it might not even be worth it to go to even higher order, right? If you remember, in asymptotic solutions, we're not guaranteed to convert. We're not guaranteed to converge as I add more terms. I'm only guaranteed to converge as epsilon goes to 0, right? So if I added another term, it might not even get better until, I go to epsilon goes to 0, because that, series might diverge. So that's another thing that's maybe the saving grace of the fact that I create this whole list of problems in asymptotic problems, is that it doesn't matter how many I generate. Sometimes I want to truncate after just a couple, and usually that helps. Okay, so, all right, so something is going on here, right? So what's going on here is that I've lost that diffusion, and in this part of the solution, diffusion still matters, okay? And think about that for a second. Think physically what's going on. We have this fluid flow that's pushing stuff here, okay? But we have to still satisfy this boundary condition here. And at some point, right, there's a concentration gradient that's big enough between here and here that diffusion term isn't little anymore, right? Even though there's a small Domkohler number out front, that gradient's so big that diffusion is not a little term, okay? And it has to, come into account. And we're not treating that fairly in the asymptotic expansion, right? We're just throwing it away, saying it just doesn't matter at all. Okay, and that's what this solution says. Oh, diffusion just doesn't ever matter. But then that doesn't ever satisfy that boundary condition. It's not worried about it, right? Because there's no other diffusive term to account for that. So somehow we need to take into account the length scale of that gradient, right? We need to account for the fact that there's just this little scale here, okay? And when we non-dimensionalize our equations, we divided by L, which was this whole big scale. We didn't ever divide by this, so that gradient in the second derivative is not really the right scale. We've done it wrong somehow. So we need to go back to our dimensional analysis and think about a new scale for this side that is fair, that takes that into account. Does that make sense? What do you think about that, Brian? Yeah. You okay with that? All right, let's put this screen up and we'll blank the thing. We'll leave this for now because we'll come back to it. So, okay, I'm going to leave this up. I guess I'll take this off too. Okay, so what we want to do now is I'm going to define we're going to do new dimensional analysis. So I'm going to find two new dimensionless quantities. The first one I'm going to call psi, which I'm going to call still CA over CA naught. Okay, the difference here is that I just generated a set of solutions for this phi. And what that we're going to find is we're going to also generate a new set of solutions for psi. And then we're going to combine them somehow to get an approximation to our total answer. So this one is going to be called an inner solution, which is going to be on the left-hand side. And this one is going to be the outer solution, which is on the right-hand side. And we're going to add them together and combine it. Okay, so that's why I'm defining this way. We'll talk more about that in a second. And I'm going to define a new variable y, which is my length variable. And I'm going to call it z divided by delta. I don't know what delta is yet, but delta is just some length scale that's going to be characteristic of that gradient. Okay, we're going to have to figure out what it is. So let's go through the dimensional analysis really quick. So if I take this and I plug it back into the original differential equation, we're going to get this really similar thing that we had last time. We're going to get dCA naught divided by delta squared d squared psi dy squared plus u CA naught divided by delta d psi dy minus k CA naught squared psi squared equals 0. Okay, I guess I didn't write up the original differential equation, but you can recognize at least here, if you remember, the original differential equation was what? Second derivative of CA divided by z squared. What was it? Plus, let's see, it was VZ, right? Which was U ECA Z minus KCA squared. That was the original differential equation, if I remember. Okay, so I plug these definitions in, plug them in for there, I get these quantities out, okay? I divide by this term into here and here. So doing that quickly, I'm going to get dy squared plus delta squared over dCA naught, UCA naught over delta, d psi dy minus another one here, d squared dCA naught, KCA naught squared, psi squared. Okay, and I can cancel terms. The CA naught cancels, the delta cancels, and I get a delta U over D. So that's delta U over diffusivity. This one here, I get one of the CA naughts cancels. That's it. And I get K delta squared CA naught divided by diffusivity. Okay, and this is like a Peclet number, right? Just like I had before. So this is a Peclet number, but now on the length scale of delta. And this is a Domkohler number, now on the length scale of delta. Okay, and so I can rewrite my final equation here using the same thing, and I'm going to get 1 over Domkohler delta d psi dy squared plus Peclet delta divided by Domkohler delta d psi dy minus psi squared equals 0. So I'm going to have the same thing, okay? And then I'm going to have boundary conditions as well. So I have psi at 0 equals 0. But I'll have psi at, did I talk about that here? It's not obvious what that should be, right? This is going to be, we had it's what? X over delta. So we know that's at, see, it's at L. So this should be L over delta is equal to 1. That's what it is, L over delta, right? Because before the boundary condition on this guy, on the original differential equation was z at 0 equals 0, or CA at 0. CA at z equals 0 equals 0, and CA at z equals L equals CA naught. Okay, so psi we're divided by CA naught, and the L we're dividing by delta. Okay, but we don't know what delta is yet, so we can't say exactly what that number is. But okay, we'll say that. Okay, so the question is, now we want to relate this Peclet delta and the Domkohler delta back to the Peclet and Domkohler number we had before. Okay, so I want to, what we're going to try and do is we're going to try and pick a delta that doesn't have the problem where we get this to be our small number output. Okay, because if we pick a delta where this has epsilon in it, then when we do our asymptotic expansion, that one's going to go away. So we're going to need to find a new delta, but we don't know what it is yet, right? We need to find it. So that's the goal, is find a new delta where 1 over the Dom polar does not equal epsilon. That's our goal. Does that make sense as our goal, Tyler? You okay with that? What do you think, Christina? Okay. So to do that, I want to how did I do this? It's kind of a backwards way. I said that the Dom polar number of L was equal to 1 over epsilon. Right, so this guy here, I'm now going to call that Dom polar using L and Pecla using L, right? It's the same thing I did. I got the same dimensional analysis here. I just have a delta. I have L's in the old one, right? And I said this was true previously, right? I said the Dom polar of L is equal to 1 over epsilon. That's what I had said last. So I said this was equal to K CA naught L squared divided by D. I'm going to multiply that by delta squared divided by delta squared. Because that's just a multiplication by 1. I'm allowed to do that. So I can, bless you, I can rewrite that as KCA naught delta squared divided by D, where I now swap the place of L squared and delta squared. That right there is my Dom polar delta, right? So that means I've got Dom polar delta multiplied by L over delta squared. L squared over delta. Okay, I can do the same thing for the Pecla number. Pecla L was equal to, what is it? It was L U over D. Is that right? L U over D. I'm going to play the same game. I'm going to make that L U over D multiplied by delta over delta, which is going to give me delta U over D multiplied by L over delta, which is the Pecla number for delta multiplied by L over delta. Okay, so then I then find alpha, which was Dom polar L divided by Pecla L. Because I knew this one was order 1, so that gives me Pecla delta L over delta divided by Dom polar delta L over delta squared. And so that should give me now Pecla delta divided by Dom polar delta, and I should get delta over L. Dividing an L over delta and L over delta squared, so I should get a delta over L.
Dr. Tree,
Yes.
when you say your Dom polar sub L over Pecla sub L, and then you go to the next step, all of a sudden the Pecla number is in the numerator and the Dom polar is in the denominator. Can you explain that to me? I'm not sure I completely follow that.
Oh, I just meant to write this. Here. Do we feel better about that?
Yes, a lot better.
Okay. All right, so if I do this, now I have a relationship between this guy and epsilon, right? And I can go ahead and think about what I want to pick. So what I have now is the following. I have 1 over Dom polar delta is equal to epsilon L over delta squared. Right? Because if I move that over and move the epsilon over, I get this relationship. Okay, and then I have Pecla delta divided by Dom polar delta. That's going to equal alpha L over delta. Okay, so now what I want to do, right? What I said my goal was to pick a scale so that I don't get 1 over Dom polar is equal to epsilon, right? So previously I had picked the scale L, right? So if I make delta L, and this is going to go back to what I had before, right? That makes sense, right? So, that gives me back the problem I did before. So I want to pick a different scale for delta. I have to think about what scales there are in the problem that I could potentially make up. And I can think of, what did I think of? 4 of them. Yes, one of them was L. Yeah, I thought of 4 that we could pick. Okay. So what scales are there? Okay. There are 4 of them. First one would be delta equals L. Okay, that's a stupid scale to pick, but let's rule it out, right? Can't do that. The second one would be, what about the scale we saw previously from the similarity problem, where I had the delta is equal to the diffusivity times some time scale. Okay, I could pick that problem. And I need a time scale here. So one of the time scales available to me is this one, 1 over KCA naught. Right? That time scale, that's the reaction rate time scale. So what this says is, this is telling me how far do I diffuse in the time it takes to react. That's sort of that length scale. Okay, so I can diffuse so far before I react. Right? Let's see what that one does. So if I do this, I have to plug in that into there and that into there and take, I want to find delta over L or L over delta, either one, to find out what that gives me. Okay, so this gives me the square root of D, and then tau is divided by KCA naught. And then I have an L, which turns into an L squared inside the square root. That gives me the square root of, let's see, what's L squared CA naught K divided by D? Well, that's exactly the Dom-Kohler number, inverse Dom-Kohler, right? Right there, that's just the inverse Dom-Kohler number, which means that's an epsilon right there. Okay, so if I pick that scale, I have picked delta over L to be the square root of epsilon. Okay, so that means that if I take this and plug it into there, what do I get? Get epsilon multiplied by 1 over epsilon. Is that right? Did I do that right or am I wrong? Am I missing something? That's right. That's fine. Okay, so that works for that one. Okay, so I get Dom-Kohler delta is equal to 1. But now I have to look at this guy, and I have an issue there because this one is, now I have Peclet delta divided by Dom-Kohler delta. That's equal to alpha divided by the square root of epsilon. So if I go back and think about this equation right here, or where did I put it? Right here, this is my thing right here. Right? If I put 1 over epsilon in there, 1 over square root of epsilon, when epsilon goes to 0, this term is going to go to infinity. So that can't be the right choice, right? It took care of this, but I also have to have, no infinities, right? Or else I have a problem. So this can't be the right length scale. It makes the convection term go to infinity. That make sense? So I have to look at it differently. So there's another one. Let me start over here then. Back over here. I think we're good on this piece now. Okay, the third scale is delta is equal to square root of d tau, where now tau comes from the convection scale, right? And if you think about what I'm doing, sort of step back for a second, what I'm doing is balancing different terms, right? So when I had this term and this term, I picked something that had to do with the reaction, and I basically made the Dom color 1, and that messed up this guy. So what I'm saying here now is, well, let me try and balance this guy and this guy and see what happens there, right? So can I pick those terms to be balanced? So we can do the same thing here. Delta over L is equal to the square root of D divided by U multiplied by L. And all of that has a 1 over L squared inside there. So this gives me the square root of D over UL. Well, that's just the Peclet number, right? Peclet L. So Peclet L, which I found over here, right? I get, what do I get? Peclet L is right here.
Isn't that the inverse of the Peclet number, Dr. Tree? If you go all the way to the left on that line?
Go all the way to the left. Is that the inverse of the Peclet number?
Well, no, you just said Peclet L is LU over D, but in the equation we just wrote, we had D over UL, and we call it the Peclet number.
Yeah, you're right. That's one over the Peclet. Okay, so I know that alpha is order 1, right? So if I know, if I multiply, let's say if I have 1 over the Peclet number, that's going to equal, let's see, 1 over alpha times the Dom color number of L. And I know the Dom color number is 1 over epsilon, so that's epsilon over alpha. Right? So now I can substitute 1 over the Peclet number for epsilon over alpha. Because I'm trying to find things where I have that epsilon scale in them so I can see if I have the right thing. Okay, so now we can look at this problem. And I have the same issue here, right? So if I go back and look at, now what is 1 over Dom color delta? Well, that's epsilon divided by epsilon. Oh, that's right, right? Now I have a square. Sorry, I'm getting lost in my own math. You're probably lost too. You can stop me if you're lost. I have this squared. Flip that over. So I have an epsilon over alpha, and I get an alpha. That's okay on that guy. But if I look at the Peclet number divided by the Dom color number, I'm going to have that one, alpha. I'm looking at this, alpha times L over delta. So I flip that guy upside down as well, and I get the square root of alpha over epsilon. And now I'm going to have alpha to the 3/2 divided by the square root of epsilon. And I have the same problem that I had before, right? So failure on the first 3 length scales I can think of, L, delta, and that delta, right? Where I have the diffusive time scale. So the fourth one's going to work out. Last one is delta is equal to D divided by L K CA naught. And you're probably going to ask, where did you come up with that length scale? And it's just the last combination of things of all the variables I could find, right? That give me length still, okay? So it's clearly some other relationship between, you know, diffusivity and the length and the reaction, right? That I plug in. Okay, different ones. So I can play the same game here, delta over L, but D divided by L squared K CA naught. Okay. That's pretty straightforward. I just put an L on both sides. That gives me 1 over the Domkohler number, which is epsilon. So now I can test these. 1 over Domkohler delta is equal to epsilon divided by epsilon squared. Now we didn't have a square root anymore. We had a squared because I have this epsilon, but over there I have a square, and that gives me a 1 over epsilon. So that's okay. That still works out. We'll see in just a second, because I can multiply both sides by that if this one works out too. Let's see, this one, then I have the Peclet number divided by the Domkohler number, and that's going to give me an alpha over epsilon. So when I plug that in, because I get Peclet divided by Domkohler, I get alpha, and I have L over delta, that gives me an epsilon there. So now I'm going to take those guys, and if I have 1 over epsilon here and a 1 over epsilon here, I multiply through by epsilon, right? So let's just replace these guys right here. 1 over epsilon and alpha over epsilon. And you might think, well, wait, you said before I had to square root epsilon, what's my problem? But I can, because they're in both of these terms, I can now multiply both sides by epsilon. And this is going to be 1, and this is going to be alpha, and this is going to be minus epsilon right there. Okay, so that I can live with, right? Now I have a 1, that term's not going to go away. That term's going to be fine, and nothing's going to blow up, and it's that term that's going to go away. So the reaction term is going to be small in that region. So what's going on physically, right, is in that region where I had, you know, I guess it's kind of like this, and then it drastically changes. What this is telling me is that diffusion matters there, and convection matters there, but the reaction is relatively unimportant in that region. So by picking these scales and rebalancing them, I've figured that there's some length scale, delta, where the reaction is less important, but these other two terms need to be balanced. Okay, and there's nothing to do but to do trial and error to find. Like, you just have to keep trying these different scales and multiply by all these sides and figure out, well, what happens if that works out. Does that make sense? So this is kind of like a lot of, I don't know if you followed my reasoning here. There's different ways to go about thinking about this. You can just also look at the thing and pick epsilon and say, let me multiply which epsilon gives me something. You can pick multiply both sides by epsilon, multiply by epsilon squared, rescale these variables, etc. You can do it a different way. Okay, but in the end, you have to figure out what is this length scale delta that I'm going to pick. Okay, that's going to give me this, you know, this new problem. Okay, did I lose all of you, or are we somewhat on board with this? I think I explained it super clear, but yes.
So this delta that we found is specific to that second order reaction. If we have like a different order of reaction or a different equation, then we have to find a different delta.
I haven't thought through the case of what happens if I have a different order of reaction. It's certainly specific to the fact that I have convection and diffusion, right? Because when I have these y squareds here, but you're saying like if I have a different order reaction, I might just have in my Domkohler number like a CA naught squareds going around. And I'm not sure if that would change the problem. So if I had a third order reaction, I'm not sure if this would change. Okay. But if I had a first order reaction, I could just solve it outright, right, with linear terms. So I'm not sure if that is the one thing that makes a difference.
Would the first order reaction not be the boundary layer then?
That's a good question. I don't know. I haven't thought about that.
Okay.
I think it will give a boundary. It still has a singular perturbation. You can just solve it without using perturbation problems analysis techniques. But when you do the perturbation technique, you could also have this be linear. You could do that if, if you didn't know about, how to do the ODE solution the other way. But you can just solve it directly because it's a linear problem. The linear problem can still have a boundary. As far as I understand. Okay, so we're getting short on time, but so what we can do now, and we'll finish this tomorrow, is we're gonna be able to take this problem right here and write an asymptotic method for it. Okay, so we're gonna take that problem right there, and we're gonna say the following. So let's see, d2 psi squared plus alpha d psi y minus epsilon of p psi squared equals 0, given psi at 0 equals 0, and psi at L over delta equals 1. Okay, and we're going to write psi is equal to psi naught plus epsilon psi 1 plus order epsilon squared. Okay, we're going to take that and plug it in here. Okay, and then we're going to see that this is going to give us a solution on the left-hand side. Okay, so it's going to turn out that this boundary condition we can now satisfy, and this one we're not going to be able to do. Okay, and then we're going to take our two half solutions and we're going to merge them together in the middle. Okay, and we'll see that that'll actually give us a good piece. Right, and so maybe the kind of takeaway here is that so this problem of having two regions of solution is indicative of, like I'll sort of summarize, is indicative of these singular perturbation problems. Okay, and it's because we've neglected the math in one part that's actually essential, right? And so you can't really do that in the whole region. And so this technique has a name. It's called matched asymptotic expansions. Okay, so you have one asymptotic expansion for one part and another asymptotic expansion for the other part. And then we're going to do a matching procedure where we basically look at this solution and say, what is it in the limit that I go to, y goes to infinity, right? Because when y gets really big, that's when I'm looking towards the right-hand side of that plot, right? And I'm going to take the other solution that I had, and I'm going to take that and I say, what happens as x goes to 0? And then I should find that they look like the same thing in the middle, and I'll be able to get an answer where they overlap. Okay? And so what happens, we're going to see in boundary layer problems, we have exactly this problem. We have convection that dominates in our outer layer, okay? And near a surface, we have diffusion that matters, momentum diffusion. And so if you write down the Navier-Stokes equation and the high Reynolds number limit, that's exactly the same problem, is that you have a region out here where viscosity doesn't matter. Okay, but in the region near the boundary, viscosity still matters, and you have the singular perturbation problem. So all of boundary layer theory is about solving these two regions, outer region with high Reynolds number stuff, and then the inner region, which we're going to get boundary layer equations. Okay, so boundary layer theory, the whole thing is just one large matched asymptotics problem. Okay, all right, so we'll finish that up next time. Hopefully start talking about boundary layers.